Good morning, everyone. Welcome to IME 470. Today is April the 20th. First, let me share my screen. And also stop the video. Okay, so in the, sorry, let's see. Single page. In the last lecture, we mentioned the concept of the tree. And again, here in this lecture, we assume that all graphs are undirected, meaning that if there's an edge, or let's say meaning that if there's an arc, then the arc must be bidirected or undirected. And a graph is connected if and only if any two nodes in the graph are connected, meaning that for any two nodes, there must exist a path to connect them. And the graph is a tree if and only if it is connected and acyclic. So for example, this is a tree, but this is not a tree, although it's connected. It is cyclic, not acyclic, so it's not a tree. And I remember I showed you some examples of the trees here. This is not a tree. Why? Because it's cyclic. For example, from one, you can find a path, go back to one. It's cyclic, so it's not a tree. And oh, by the way, this is a real life tree. Although strictly, I realize I cannot just call it a binary tree. For example, consider this node. Let me take out the annotate here. Okay, for example, consider this node. Suppose this is node. It has a lot of children. Children means the node after it, connected by it. So strictly, it's not a binary tree. But if you have a look at this kind of small trunks, and then you can see it really looks like a binary tree. And I also remember I promised you that I'm gonna find it in Google, right? Okay, let's do it. Let me go to Google Map first. Oh, let me put it here. So in the Google Map, let's search. Let me see. Loyola San Diego. Here you go. Later, if you have a chance, you're highly recommended to visit the tree here in the Loyola Cove. It's, I think, let me see. I think it's around here or here. Let me see whether I can. Let me see. It's here we go. Here we go. This one, this tree, it's here. Let me see whether I have some better views of it instead of like this way. Whether I can see, for example, from here. What is this? Okay. Where is it? Let's find the other one. This tree is very special. Very, very beautiful. Trust me, really very. Here we go. This tree, almost the same angle as my picture. Let's see. Look, very similar. From this one, from this direction, smaller. So okay, and even the White House, not the White House, the house in white color is also here. So okay, here we go. Great. We've located it. So it's right here. Go to Loyola. You can search Loyola, which is a very, very famous cove in San Diego. And it is around here, this part. Okay, so this is a very beautiful, almost real life, almost a binary tree. And amazing, really amazing. At that time, I told my roommate, because I came with my roommate, that I'm gonna use it to teach the concept of graph theory, especially trees later. So that's also the reason why I put it here. Okay, so what is, this is the definition of a tree. And the next one is the definition of spanning tree. That for a given undirected graph, G equal to VE, a spanning tree is a tree that includes all vertices of the graph. Be careful that the G itself doesn't have to be a tree. And in the next slide, I will introduce some examples of the spanning tree. And we are more interested at actually at not only the spanning tree itself, but the minimum spanning tree, MST. It is a spanning tree with minimum total weights. By the way, it is possible, although not very common, that a graph could have multiple MST, multiple minimum spanning trees. Let's have a look at some examples. So suppose this is my primal graph, and clearly this is not a tree. Okay, then let's have a look at this. This is a subgraph generated from the primal graph. By subgraph, what I mean is that I can, I generate a graph from the primal graph, but I remove several nodes or several edges, and then it's going to be a subgraph. So clearly, this is a subgraph. Why? Because I copy and paste, from the primal graph, but I removed this node, this edge. You can see this edge is gone, no 2, 4, so that it's clearly a spanning. It's clearly a generated graph. But this graph, it's not a tree. Why not a tree? Because again, for trees, it's a graph which is connected and acyclic. Have a look at here. Yes, this graph is connected, but it's cyclic. Why? Because have a look at here, 1, 4, 5, 3, 1. See, I can go back from 1 to 1. It's cyclic. So this is not a tree, okay? And then have a look at this. Is this a tree first? Question. Yes, this is a tree because it's connected and it's cyclic. Yes, but this is not a spanning tree. Why? Go back to the definition here. A spanning tree is a subgraph generated from G that includes all vertices. It must include all vertices of the graph. Let me change the color, red color. And then come back here. We can see this does not include node 5. See it? There's no node 5 here. So this is a tree. It's a generated tree from the original graph, but it is not a spanning tree of this graph. Okay, how about this case? In this case, yes, it is a spanning tree. Why? First, it's a tree because this graph is connected and acyclic, very clear. So it's a tree. And it is indeed a spanning tree of this graph. Why? Because it's generated from this graph, and you can see it includes all nodes. Okay, let me ask you a question. What if I make it in this way? For example, I add one edge here, and I randomly give it a number, whatever number. Let's say, what's the date today? Today is April 20. So for example, the weight is 20. What if I have this graph? First of all, is it a tree? It's not a tree. Why? Because it's cyclic, right? And the second thing, very important, is this is not a subgraph of this graph. Why? Because in the original graph, there's no edge 1, 2. And here you added one edge 1, 2. Be careful that a generated graph, you cannot, as a subgraph, you cannot have some extra edges or nodes that do not appear in the primal graph. So you can only be a subset, no matter in terms of the nodes or in terms of the edges. You can only be a subset of the of the notation. Let me write it here. Of the notation G equals to V and E. Okay, where V is the vertex set and E is what? E is the edge set. So for example, suppose you have a subgraph here, a subgraph G equals to, let's say GS equal to VS and ES as means subgraph. If in this case, then we must have what? We must have VS as a subset of V and ES as a subset of E. We cannot have something, for example, exist in the VS but does not exist in the V. Then something's wrong. Then that becomes V is a subset of VS. That's wrong. A generated subgraph, you must be everything, no matter vertex or edges. it must be a subset of the original graph. Okay, so that's why I cannot have some extra nodes or extra edges compared with the primal graph. And indeed, this is a spanning tree. How about this one? This one is also a spanning tree. Why? Again, it is a tree. And the second thing is what? It includes all notices, all vertices from the primal graph. So yes, it's a spanning tree. Okay. And one thing I need to mention is that this tree gives a total weight of 17. How to calculate it? You just count the weight, the sum of the weight of the edges. 4 plus 3 plus 3 plus 5 plus 2 equal to what? Equal to, why I feel it's equal to 60? Yes, it's equal to 17, okay? And this is also a spanning tree, but the weight of this spanning tree is 14. You can simply, verify it by summing all of the weights. 4 plus 3 plus 3 plus 2 plus 2 equal to 14. And how about this? This is also a spanning tree. Why? Because first, it is connected. Second, it's cyclic. And third, it includes all node vertices of the primal graph. And indeed, there's no this kind of like extra, edges or not. Everything is a subset of this graph. So it's a subgraph. And hence, it's indeed a spanning tree of this graph. However, the weight here is 13. You can just simply add it, and you're going to see. And this is indeed the minimum spanning tree of this primal graph. Any questions here? Please feel free to ask me questions if you have any questions. Make sure you unmute yourself, otherwise I cannot hear you. Any questions? No question? Okay, give me 1 second. Let me have a look at here. Where's my Zoom meeting control here? I cannot find my Zoom meeting control. That's interesting. Oh, it's here. Okay, so let's continue. A single page. Now the question is how to find the spanning tree. And also there's a question about, let's say, what is the meaning? What is the motivation of having the spanning tree? Okay, having the minimum spanning tree. Let's have a look. The very first application is communication network. Something, for example, Verizon, AT&T, Sprint. By the way, personally, I like Verizon. The signal is really much better than the other two. I don't know what are your choices. T-Mobile and Sprint looks very popular in Fargo. Anyway, however, if you're living in some area like, for example, Montana, maybe you would really prefer Verizon because the signal of Sprint in Montana is really, at least was really bad. I don't know this year. 2 years ago, I visited Yellowstone and also somewhere in Montana. Oh my goodness, completely around Yellowstone, even not even in the Yellowstone. I was using Sprint at the time and completely no signal. Really bad. Anyway, so the purpose here is to connect all areas based on a given graph. So consider, for example, this is, let's say, for example, this is Fargo. Communication, network of Fargo, and each node here includes one area, a small, let's say, street or some unit, a community, for example, small communities. And what I want to do is that I want to connect all of them. Why? Because I want to guarantee, for example, a person in this place can call a person in that place. Any places, in this graph, I need to make sure that they're connected. Otherwise, let's say people pay for your service, and you do have signal, and for example, suppose this one is disconnected. For example, suppose I don't have this edge. Then what's going to happen is that people living in this area gonna be isolated from the big area. then there's something wrong. People here are gonna complain, hey, I pay for you and you didn't, give me the service, right? That's the reason why I need to guarantee that this graph, the communication network would be connected. Then the question is, for example, why don't you just apply the original graph? For example, looks like this way. Why do you need a spanning tree? Because I want to be economic. Because suppose, think about this. Suppose, let me make it a bit bigger. Suppose my graph is in this way. For example, let's make edges like this. Suppose all of these kind of things are connected. So this is also a connected graph. Why don't we use this? Because it's not economic. Why? For example, consider a person A is here, and for example, consider a person B is here. The point, let me see. A person B is here. This one, not that one. Sorry, it's very difficult to use mouse. Okay, so in order to make A and B connected, in the original graph, we can go which way? We can go this way. We can go A to this one to this one, and then this one to B. See it? Or vice versa, from B to A, it doesn't matter, because it's an undirected graph. We can connect in this way. So yes, A can connect to B. But now we also, build the network communications directly from A to B. What's the point of this? Of course, you can increase the reliability, and maybe it can be a bit faster. Assuming, for example, A is in the US, B is in China, for example. So if you build a direct connection, maybe faster. But in relatively small area, let's say, AT&T, Sprint, or Verizon, their main service is what? As in the US, right? Or let's say, suppose, as we mentioned, that this graph is, the whole graph is in Fargo. I don't have to, really build direct connection from A and B, because, it won't really, delay really too much. The delay may be 0.1 second. That most people cannot, or even 0.01 second. Most people cannot realize it. So it doesn't matter. However, if I want to build communication, this kind of edges, for example, this kind of red edges, each edge will cost me a lot of money to build the communication, the network. And that's the reason why I don't have to, really build something, connect, each other. What I need to do is just to have a spanning tree. And that's enough. From this one, I can guarantee any two nodes from here to here, for example, any two nodes here to here, in this tree can be connected. For example, a node here. See it? So in this case, yes. And one minimum spanning tree, the same reason, for saving money. And hence, this is a great application in this kind of network, in this kind of communication problems. Okay, it helps us to find an efficient communication network. And the weight ij here gonna be the cost. This cost could be distance based, or let's say material based, or whatever, or let's say the real money cost. It doesn't matter. And again, MST is to find the minimum cost here, such that all the nodes can be connected. Any questions here? This is a very, very important application of the minimum spanning tree. And indeed, the problem of minimum spanning tree was proposed, I forgot which year, 1950s or 1960s, I think. At that time, if I remember correctly, by someone in AT&T. At that time, they had a lab, and they were planning how to build the communication network in the US. At that time, computer was not that popular, not as popular as today. At that time, 1960s, not most families actually didn't have computer. This kind of military or research labs, they had computers, and they proposed what is an efficient and economic way to build this kind of systems, and so that people in the network can be connected to each other, and meanwhile we can save them money the most. And here we go, minimum spending tree. Then the problem is how to solve the minimum spending tree, because the problem looks beautiful. You can even apply it to the whole world. Any two places from, for example, not really any two, let's say in many places, most places in the world nowadays, we have a communication. You can directly make a phone call, or easier, you can connect to the internet, right? And we can have, let's say, video call, online video call in the whole world. Then the problem is how to solve it. And in this lecture, we're going to introduce two very important and famous algorithms, Prim's algorithm and Kruskal's algorithm. They're designed for solving MST problems. Any questions here regarding the application of MST? No question? Okay, let's continue. Oops. For Prim's algorithm, the basic idea is to gradually add nodes to set P. So here we have, for Prim's algorithm, we have two sets, set P and set MST. I'm going to gradually add nodes to set P by including the minimum weighted edge connected with nodes in P and to the MST set until, connected with nodes in P. I'm going to add the edges to MST. P is a set index set for nodes, and the MST is an index set for edges until all nodes are in P. And the MST again is to store the minimum spanning tree finally. And the idea can be summarized as to find the best neighbor for existing residents. Residents means nodes in P. So a summary is here. In initialization, I randomly select one node to start. So for example, suppose I select node I0, and then I'm gonna write P equals to I0, and MST is empty set. And now I'm gonna add edges to MST and add nodes to P. So if all nodes are already included in P, I'm gonna stop, and MST is the minimum spanning tree for the graph. Otherwise, I will find the minimum weight Wj such that I is already a resident, meaning that I is in P and the J is in V minus P. In other words, I want to find this. I want to find this one. Wij equal to the minimum of Wij such that I is in P and the J is in V minus P. And then I'm going to add this new node, the J star, to P, and add this edge I star J star to MST, and a loop, do the loop of repeat step number one. This loop means repeat step number one. If there's a tie, then I just randomly choose an edge. It doesn't matter. Why? Because the next time I'm gonna choose the other one. Let's have a look at an example. I think via example it's gonna be more clear, and then we are gonna go back to review Prim's algorithm. Let's consider this graph, a very simple graph to make my life easier. So in the very beginning, let's say step number 0. Okay, so this is the original graph. This is even before we start. So in the original graph, P is empty, and the V minus P is everything, meaning the nodes are 1, 2, 3, 4, 5, and my NST is not applicable as well. So here I wrote not applicable to differentiate empty set, meaning that we haven't started yet. This is just the original graph. Okay, then step number 0 is initialization. We randomly choose one node. So without the loss of generality, I choose node 1 to start as the starting node, P equal to 1. And then set MST to be empty set. And then the result is going to be here. So I use the red color to indicate that this node is selected. And now node 1 is in P, and V minus P is 2, 3, 4, 5, and MST is still empty set. Okay, here what I'm gonna do is that I'm gonna choose the minimum weight such that I is in P and the J is in V minus P. This actually means what? This actually means you want to find the closest neighbor for the residents here. And currently I have only one resident, meaning that I have only one node in P. So I have which are the edges connected to 1 so that I can find its neighbors. You only have 1, 2, and 1, 3, right? And the W12 equals to 2. W13 equals to 3. So the minimum one is what? Is 2. So yes, I'm gonna add edge 1, 2 to MST, to set MST. And then I'm gonna add node number 2 to P. Here you go. I'm a bit too fast, sorry. I'm one step faster than the slide. So let me see here. So I add this to this, and then I add edge 1, 2 to MST. Yes, here we go. So I get this graph. Now I have P equals to 1, 2, and V minus P equals to 3, 4, 5, and MST is 1, 2, edge 1, 2. Now what shall I do? Similar. Among all my residents, which are nodes 1 and 2, I'm gonna find the minimum edge. So totally, what are your choices? Your choices are here: 2 to 4, 2 to 3, 2 to 8, and 1 to 3, right? And then you want to find the minimum one among all of this. And clearly we have a tie. We can either choose 2, 4 or choose 2, 3. And it doesn't matter. Why? Because no matter you choose 2, 4 first or 2, 3 first, the next time you're going to choose the other. For example, suppose here, let me see, I chose 2, 4. Suppose I chose 2, 4 here. I chose 2, 4. So in this case, I'm going to add a node number 4 into P and add edge 2, 4 into MST, right? I'm going to do this. Okay, then what's going to be the next stage? Here, have a look at the graph here. My P equals to 1, 2, 4. And by the way, I use red color to continue my notation. I use the red color to indicate the most recent added node, and the green color to indicate, the nodes and edges are already fixed, or nodes in P and edges in MST. Okay, so if we fixed 4 first and added 2, 4 to MST, what is your next choice? Your next choice will be 2, 3. See it? Because among 1, 2, 4 and all its neighbors, you want to choose the minimum weight. See it? And you're going to choose this one. And the same, what if, for example, here, I didn't choose 2, 4. For example, suppose I choose 2, 3. Okay, so then I'm going to add 2, 3 to MST, and I'm going to add a node number 3 to P, right? Suppose it's in this way, okay? Let me change the color to be red. And let me make it a bit bigger. Okay. Suppose I did it this way. Then what's going to happen? Among nodes 1, 2, 3, you're going to choose the minimum weight, right? And what's going to be, you're going to see, again, here, I'm going to choose node 4. See it? So it doesn't matter which one you choose first, which one you choose later. Sooner or later, you're going to get to the other one. That's the reason why if there's a tie, you can just randomly choose one. It doesn't matter, okay? So let's continue this example, this selection that I choose 4 first. And then in the next step, I'm going to choose 2, 3, as we have already mentioned. So in this case, I'm going to add a node 3 into P, and then I'm going to add edge 2, 3 into MST, which is here. Okay. Now I added node number 3 and edge 2, 3 is here. And now V minus P is only 5 because I've already fixed 1, 2, 3, 4. Okay. Finally, let's have a look at here. Add a look at here. Among all edges, which one can I choose now? I can choose, let's say, this one, or this one, or this one. I have only 3 choices. Why? Because you need to guarantee that I as Wij such that I is in P and J is in V minus P. Okay, for example, you cannot choose this one. Why? Because in this case, both I and J would be already in P. Remember here, both node 1 and 3 are in P, so you cannot choose this edge. And the only possible cases is here, these three, right? 2, 5, 4, 5, or 3, 5. And among these, I'm going to choose the minimum one, which is this one, 4, 5. See it? Okay, so finally, I'm going to get this. I'm going to get this result. And very clear, after this step, I'm done. Why? Because P has already included everything. And V minus P is empty. And in other words, all nodes are already fixed. And hence, my MST is this. 1, 2, edges 1, 2, 2, 4, 2, 3, and 5, 3. And here we go. This is the primal graph, and this is the MST. And the total weight is 12. And very clear, you can verify this is indeed a spanning tree of this. This is very easy. And if you want to try, you can try it by enumeration after the class, of course. You can find that this is indeed the minimum spanning tree. Okay. Any questions here? I think this Prim's method is actually really simple. Any questions? So let's review the process again after this example. Initialization, I randomly choose a node, say node number I0, and I start from this node. I add this node I0 to P and the MST to be empty, the empty set. And then the optimality test is if P already includes the whole graph, all vertices of the graph, then we stop. And MST set is the final minimum spanning tree for the graph. Otherwise, I'm gonna do a for loop. What is the loop? That I'm gonna find the minimum weight Wij such that I is in P and the J is in V minus P. In other words, I want to find something like this. Suppose the corresponding choice is node I star in P and the J star in V minus P. What I'm gonna do is that I'm gonna add node J star into P and add edge I star J star into MST. See it? The same. So for example here, the I in this graph, the I star J star is 1, 2. So I added node 1, 2. In this graph, I choose 2, 3. So I added this 2, 3. In this graph, I choose 2, 4. In this graph, I choose 2, 4. So that I add 4 into P and I add edge 2, 4 into MST. And in this graph, I choose 2, 3. So that I add node 3 into P and edge 2, 3 into MST. And in this graph, I choose 3, 5. Okay, so these are the choices of I star, J star. And again, if there's a tie in Wij, the minimum one here randomly choose an edge. For example, here. Currently, in this step, you have 2, 4 and 2, 3. Both of them are the minimum. You can just randomly choose one. It doesn't matter. Okay, any questions about Prim's algorithm? No? Okay, as an exercise, everyone please take out a piece of paper and then use Prim's algorithm to do this exercise. I will wait for, let's say, 2 minutes, and then after it, let's do it together. Please take a piece of paper, really do it. Let's start from node 1 to make the life easier. And I'm gonna ask, let's say one volunteer to, we don't have a whiteboard, to show the step. Let's say each step, which node and edge would you choose? And again, if the answer is mostly correct, I'm gonna add you bonus points as we mentioned before. Please really take a piece of paper and then try to find out the result by yourself. Do not wait for me. Do not wait for the answer.
I think I got it.
Hello?
This is Patrick. I think I have the answer.
You all ready? Let's wait for one more minute. Who was speaking, by the way?
Patrick Burns was speaking.
Hey, Patrick. Okay. Yes, let's wait a little bit more, just a little bit, and then I will let you tell me the answer. And let me also put this one here. We're gonna start from node 1. Okay. Yes, Patrick. Please tell me your solutions step by step. Do not directly give me your answer. Hello?
Okay.
Yes.
So we look for our minimum of our choices. We have either 5 or 7. We're going to choose 5, which leads us to 3.
Yes, very good. Slow. Give me 1 second. Be slow. Okay. Yes. And then
at node 3, we have choices between 9, 15, and 6.
Patrick, one minute. Although yes, I know what you're talking about. Your choice here, you're gonna choose this one, right? It's correct. But be careful, Patrick. What you are choosing is not only the neighbor of node 3, okay? What you are choosing is the smallest neighbor between 1 and 3. Not between. The smallest neighbors of any edges can connect to 1 and 3. Suppose excuse me. Suppose my number here is 5.5. Then you're gonna choose 1, 2 rather than 3, 6. You know what I mean? The reason you can choose 3, 6 is because here 6 is less than 7. In other words, you need to take this 7, edge 1, 2 into consideration as well. Okay. So yes, at this stage, I'm gonna choose edge 3, 6. You're absolutely correct. Continue, please. Hello?
Sorry, I got a temporary on mute. So I'm a little bit wrong towards the end, but so we'll still choose to go to node 6 from node 3. And then from node 1 to node 2, because that's our next minimum.
Very good. Yes. And continue, please.
Then we look at all of our options. Node 2 to node 5 is now our least.
Very good. Yes. Continue.
Then we'll go from node 5 to node 4.
Mm-hmm. Yes. 5 to 4. Yes.
And then the quickest route to 7 is through 9.
So, through 9. Oh, you mean 5 to 7?
5
yes. Very good. You are absolutely correct. Very good, Patrick. Thank you. To encourage the class activity in the online teaching, how about this? I'm gonna give you double bonus. Double bonus. In other words, I'm gonna add you 2 points instead of 1 point in your final grade. Thank you very much, Patrick. And it's gonna be applied to other future this kind of questions as well. I will have more in the future, and every time I'm gonna add 2 points. These 2 points doesn't mean just 2 point, in your final exam something. It's even worth more. Why? Because final exam is worth I forgot 30 or 35 points, right? These 2 points directly works in your cumulative. In other words, you directly get 2 points. You know what I mean? It's a lot actually. Okay, very good. Everybody gets the same answer, the idea. What Patrick just did was absolutely correct, step by step, okay? And let me use Ctrl-Z so that, I'm lazy to redo it again so that we can see the steps. So let's repeat it. We start from node number 1 first, right? And then we're gonna choose the minimal neighbor of node 1. And very clear, I'm gonna choose node 3 because I only have 2 choices, 5 and 7. This 5 is smaller, so I'm gonna choose 3. And then I'm gonna choose the smallest edges of node 1 and 3. So currently I have several choices. 1, 2 with weight 7, 3, 2 with weight 9, 3, 5 with weight 15, and 3, 6 with node 6. Of course, with weight 6. Of course, I'm gonna choose node 6. In other words, what I'm doing is to add 6 into P and add 3, 6 into MST, so that I'm gonna add this point, this weight into the MST. Okay. Oops. Too fast. And then in the next step, you're gonna add the minimum weight to the set to the nodes of 1, 3, and 6. Then which one is the minimum one? Clearly, you're going to choose 7 because your total choice is 7, 9, 15, 8, and 11, in which 7 is the smallest one. So yes, I'm going to choose 7. And correspondingly, I'm going to add node 2 in P and add edge 1, 2 into MST. And then the next one, your total choices will be 2, 4 with weight 8, 2, 7 with weight 5, 3, 5 with weight 15, 6, 5 with weight 8, and 6, 7 with weight 11. So 7 is the smallest one. I'm going to choose this one and add a node 5 into P, edge 2, 5 into MST. Similar, your next step will be this one. It's the smallest. Oops. And then I take this one. And the next step, you only have 2 choices, which is 5 to 7 or 6 to 7. Be careful. You do not have, for example, 4 to 2, 5 to 6, something like this. Again, your choice would be what? I is in P, is J is in V minus P. Currently, your P is 1, 2, 3, 4, 5, 6, and your V minus P is 7. That's the reason why you can only have 2 choices, either 5 to 7 or 6 to 7. And because 9 is smaller than 7, 11, so I'm gonna choose 5 to 7. Okay. So finally, the one in red is my MST to this graph. Any questions? No question? Okay. Very good. The next one is cruise course. Anyway, due to time limit, I'm not gonna start cruise course algorithm because I know I cannot finish it. Okay, so let's stop our class a bit earlier today, and that's everything about the class. Thank you very much. By the way, please remember to start homework 5 or 6, homework 5, and the due date is this Friday. Thank you very much and have a good day. Bye-bye.